Why were massive early stars so much bluer than our own sun? The answer lies in these curves here. You see, at a higher temperature, the peak wavelength shifts to a smaller value. Blue wavelength light is shorter than red, for example, or orange. And so these massive blue stars in the early universe were much hotter than our sun. This is Wien's law. This is the equation that explains what the peak wavelength of the light is. That's lambda max. That's essentially the color that the star will be because it peaks at that wavelength. B is just a constant of proportionality that's measured experimentally, and T is the absolute temperature. You can actually use this formula to figure out what your peak wavelength is. Pretty cool. And you'll see that it's in the infrared range of radiation. Today I'm going to talk about an apparent paradox in relativity and its resolution. That's right, today we're going to talk about what is the length of a photon. So here we have the formula for length contraction. L0 is the length of the object in its moving frame. L is the length of the object as measured by a person at rest. As you can see here, the formula will show a shortened length for the object if it's measured in a rest frame, because the original length L0 is multiplied by that factor in the square root, so it's less than 1. But a photon goes at velocity of c. Having a look at this formula again, that would give 0 for the term inside the square root. A length of dun 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 0? How could a photon have 0 length? It doesn't. This formula doesn't work for a photon because the photon has no reference frame where it's at rest. So this is only valid for massive particles. Does a quantum particle, like an electron, ever lose its spin angular momentum? No. Incredibly, unlike a classical object that's spinning about its axis and can lose its angular momentum due to a variety of interactions like friction or even gravitational interactions, if we're talking about the moon, which at one point did spin about its axis but became gravitationally locked. Unlike those objects classically, the quantum objects that have this intrinsic spin, they never lose this spin. It's like a source of energy that never depletes. It's intrinsic to them in the same way that we think of mass as being intrinsic to an object. So what makes this happen? Well, this is due to the quantum mechanics of the objects. And we can encapsulate this in the wave function and saying that the wave function is either symmetric or anti-symmetric. Is it wrong for me to say that spin angular momentum is associated with energy? I mean, after all, energy and momentum are two different things. So am I being misleading by saying this? No, I'm not actually. And I'll explain why right now. Because the spin orientation at the quantum level is responsible for energy at a classical scale, magnetic energy. In fact, when you have two magnets interacting with each other, the magnets on your fridge, for example, that is because of the alignment of the spins themselves. So yes, angular momentum is different than energy. However, there is a magnetic energy associated with spin angular momentum, and you can see it macroscopically in magnetism. Another reason why we can't say that the electron is orbiting the nucleus in an atom is because it doesn't have a definite orbital angular momentum. It has a superposition of different possible angular momentums. The eigenstates are in a superposition, and then if we disturb the electron and make a measurement, then it has one of these values. But we can't treat it as if it has a definite value because then the mechanics of it doesn't work out properly. So we have to treat it as if it's in a superposition of different angular momentum states, both for orbital angular momentum and spin angular momentum. So it can actually be spinning up and down simultaneously. That's incredible, and that's impossible classically, but happens in quantum mechanics. Hi everyone, this is an update. I've taken a little break from the videos because I'm currently working on a new book, my first book actually, and it's going to be amazing. I'm going to have a whole chapter on the starting point of the universe, start to finish. The second chapter, there's going to be a whole chapter on time itself, basically how time is defined in the different theoretical formulations from statistical mechanics to quantum mechanics to general relativity and how those need to come together to be unified. And then there's a whole chapter on black holes, there's a whole chapter on dark matter, a whole chapter on dark energy, and then there's going to be multiple chapters on galactic simulations and how you can actually do analysis of these. I'm going to talk about the main ones like Illustris and how you can actually access these and actually do your own analysis and learn how to be an astrophysicist. So stay tuned. If you give me just a few seconds, I can teach you everything you need to know to understand the concept of parallel universes. Ready? Here goes. The plot you're looking at here is called a space-time diagram. There's two cones. One of them is the future light cone and the other is the past. At any given point in time, we're located at the origin. Now, when the Big Bang happened, you can think of it as the moment when these cones were created. But at the same time, there could have been other light cones created, creating other universes. But, as you can see here, there's three distinct regions. There's the time-like region, which lies within the light cone, the light-like region, which is at the actual surface of the cone, and the space-like region. You guessed it, light travels on the light-like region, we travel within the time-like region. But to travel to the space-like region, where the other universes are located, you'd have to go faster than the speed of light. What is this crazy object behind me? This is Io. It's a moon of Jupiter, and it orbits roughly 420,000 kilometers away. The colors that you see are the result of all these volcanic eruptions. You see, it has over 400 active volcanoes that regularly erupt and litter the surface with sulfur and sulfur dioxide. And the eruptions can go as high as 500 kilometers or 300 miles above the surface. What causes all of these volcanoes to exist is frictional forces within the interior. Plates push up against each other just like they do on Earth, causing volcanoes. But the forces are due to tidal forces between Jupiter and its other moons. Was there a planet that was discovered with a pen and not a telescope? Yes. It was one of the biggest mysteries in the 1800s. John Couch Adams and Urbain Le Verrier looked at the orbit of Uranus, and they found that there was something wrong with its path. It wasn't orbiting in the way predicted by Newton's laws of gravity. What they postulated was, what if there was a missing planet that they didn't know about that was somehow affecting its orbit? What they did was they took data of Uranus and they compared it to the path that it would follow if there was no other object there besides the sun and the planets that we knew about. And what they found was its orbit could only be predicted if there was another planet somewhere further out influencing it. They actually calculated the mass and the coordinates, and they sent this to an astronomer who discovered it with a telescope. Every 300,000 or so years on average, Earth's magnetic fields do something crazy. They change polarity, meaning what was once the north magnetic pole becomes the south magnetic pole, and vice versa. But why does this happen? Well, it turns out that Earth's magnetic field is caused by its iron core, and this core is rotating. Now, the process by which the magnetic field is generated essentially involves rotations of magnetic moments. And what happens is there's a magnetic field that is continually created, but it's also continually varying, meaning at any given instant, the magnetic poles are always shifting. But incredibly, over time, these shifts can cause balances to go off, and we can completely shift polarity. To understand global warming, you really need to understand quantum mechanics. It turns out that CO2 and all other molecules can only absorb light of certain frequencies. They have energy levels, which means that they can only take in energies at certain wavelengths of light. It turns out that CO2 really likes the heat frequencies. And what happens is the light will come up and it will change the energy level of the CO2 by the CO2 absorbing it. then the CO2 will do another thing. It will re-emit the light in some random direction. The fact that it's random is also a quantum mechanical effect. But what that means is there's a 50% chance that the CO2 will just re-radiate the light back down to the surface of the Earth instead of out into space. So there's this endless cycle of heat coming up, getting absorbed by the CO2, and then being re-radiated back downwards. At a temperature of 464 degrees Celsius, Venus is the hottest planet in the solar system, but it's not the closest to the sun. You would think that Mercury, being the closest, would be the hottest since it gets the most intense flux of solar radiation. But actually, it has very little atmosphere, so there's no way for heat to get trapped. Meanwhile, Venus has tons of greenhouse gases of CO2. It has an extremely thick atmosphere, which means that it's very good at trapping heat and warming it. So yes, Venus is one of the strongest pieces of evidence that we have that CO2 does contribute to global temperatures being much higher, because Venus is not the closest to the sun, yet it is far hotter than another planet that gets way more radiation. But the difference is that it has an atmosphere of greenhouse gases.